So we are discussing about MOOPS, multi-objective optimization problem. So especially in MOOPS, we are discussing about a type solving one technique of solving MOOPS problem, which is called as NSGA. Yeah. So this is what we are discussing, which is non-dominated sorting procedure. So basically, what we have discussed in the sense, it will identify the various non-dominated front, or you can call it as Pareto optimal front. First, it will identify the first Pareto optimal front. After identifying all the individuals lying in the first front will be removed. Once the first front is removed, then it can identify the next front. Then it will remove the next front also. Then it can identify the third front. Then it will remove that also. Then it can identify the next front. So on and so forth. It continues until it identifies all the solutions. Okay. That is the overall working procedure of the algorithm. So the set of solutions which are lying in the given front, they are uh, they are they are non-dominating each other. That is, you cannot say that one solution is better than another solution. So they are all in the same level. So that we are calling it as non-dominated set. And the complexity of this algorithm is order of mn square, where m is the number of objective function and n is the population size. So So in this example, if you see 3 and 5 are in the non-dominating set, 1 and 4 are in the non-dominating set, 2, even though there is only one solution here, it is also in a non-dominating set. So first, this algorithm will identify this front, then it will remove these solutions from the entire solution space, then it can identify this front. Okay. Then after removing this also, then it will identify this front. Okay. So this is how this technique works, and after identifying the after identifying the non-dominating front, rank will be assigned. So the non-dominating front which will be identified first, the all the solutions which are lying in the first non-dominating front will be ranked as 1, and all the solutions which are lying in the second non-dominated front will be ranked 2, so on and so forth. And based on this rank, dummy solutions will be assigned. That is, all the individuals or solutions lying on a same non-dominant front will be assigned with same, what you call, dummy score. Okay, they all will have they all will share a particular dummy score, dummy fitness score. All the individuals lying in the given non-optimal front or non-dominating front, they will share the same uh, dummy fitness score. Okay, but here the problem is, say for example, a given non-dominating front, it contains many solutions. Say it contains 10 solutions, but say from this non-dominating front we want to identify 2 solutions, and we want to choose it for reproduction in the next round. We want to perform crossover or mutation, whatever it may be. Now the algorithm says that all the solutions lying in this front are non-dominating. That is, every solution is same as every other solution. So now how are we going to identify two individuals, two better individuals or better solutions? How are we going to do that? So for that, we are there is one proposal. So that is what is called as sharing the coefficient. sharing the coefficient. So given the non-dominating front and set of solutions in the non-dominating front, we are somehow going to identify like we are going to basically identify the diverse solution. How we are going to differentiate like this solution is different from this solution, so that if what you call if crossover is done between these two solutions, we may get a better solution. So in the same non-dominating front itself, we want to differentiate the solutions like here the difference is diversification. How one solution is diverse from other solution, that we want to identify. Okay, so that we can have a proper mechanism for selecting the individuals for the next round to perform mating or crossover or any form of reproduction. Okay, so for that we are using a technique that is called as sharing the coefficient. So this, I think this we have not discussed clearly, so I'll explain this here once again. So I want everybody to listen properly. So this sharing the coefficient, what it does in the sense, so here dij represents the distance between two solutions. So this is one solution and this is one solution. We are going to identify the distance between the two solutions. How we are going to identify in the sense, for that what we are doing, we are just using this formula. It is 1 minus dij by t shade. Okay, so the dij is nothing but the dij is that particular individuals. Dij is the distance between these two. This is ith solution, this is jth solution. So dij is nothing but the distance between these two solution. Okay, and this distance is divided by t shade. What is t shade? T shade is the radius, or how much distance, how much maximum distance we consider. That is what is called as t shade. So t shade is the maximum phenotype distance allowed. So maximum how much distance we allow. So it is not that we allow everybody, some distance will be there. Okay, so accordingly, so if this solution is lying within that distance, with that is if it is less than t shade, okay, then we will consider this style of doing. That is what we do is 1 minus dij, which is the distance between I and jth solution, divided by t shade the whole square. So this method we will follow, this logic will apply if the distance between ith solution and jth solution is less than t shade. Otherwise, suppose if ith solution and jth solution is not less than t shade, then in that case we will make that as 0. Okay, like that we will look for all combination, all possible combination. Suppose in this front, if there are 10 solutions are there, say this is first solution, this is second, third, so on and so forth, up to 10 solutions. Then you have to compare first solution with the second solution. Check the distance, whether the distance between the first and the second solution is less than t shade or not. T shade is the phenotype distance which we consider. That is the maximum phenotype distance which we consider. Beyond that we don't consider. Okay, so t shade is the maximum phenotype distance that is allowed, or that we consider for calculating. So if the distance between I and j is less than t shade, then apply this formula. That is 1 minus dij by t shade the whole square. Okay, suppose when you, so this is between the first and second solution. Similarly, you should do for first and third. When you do for first and third, suppose if the distance between the first solution and the third solution is greater than t shade, in that case sh of d13 will be 0. Okay, like that we calculate for all solutions. So there are 10 solutions, means you have to calculate d12, d13, sorry, sh of d12, sh of d13, sh of d14, so on and so forth, up to sh of d1 comma 10. Okay, so or you consider 1, so 1 comma 2 means between 1 and 2, 1 comma 3 between 1 and 3, 1 comma 4 between 1 and 4. So d1 comma d10, right? Not only that, it's not yet over. So this is only from first solution we have identified the distance with other solutions. Similarly, you have to do for second solution. sh of d21. Okay, maybe that is same as 1 2, so that can be ignored. 2 2, that is you cannot do with the same solution. So sh of d 2 3, distance between second and third solution. sh of d 2 4 2 5, so on and so forth up to 210. Okay, again similarly 3 1 3 2 3 4 up to 310, 4 1 4 1 4 1 4 2 up to 410, right? Like that 10 1 10 2 up to 10 9. So like that you have to identify all the solutions, right? So basically how many solutions you will get? So basically how many values of sh of dij you will get if there are 10 solutions in this Pareto optimal in this front? Yes, could you answer? How many sh of dij values you will be getting for each front? How many, I mean for the first solution, how many values you will get? 9. Okay, similarly for second, yeah, 90. Okay, but again no, in the second round one will be reduced. Are you getting? Because you 1 2 already there in the first round, right? So 1 2 will be okay, maybe it may not be same, right? So okay, we can consider 9. So 9 into 10, there will be 90 values of sh of dij you will be getting, right? Okay, yeah, see 1 2, if it is the distance between 1 2 and 2 1 will be same, right? So I mean 1 it will be reduced in every round. Are you getting? First round 9, second round it will be 8, third round 7. Hmm? Yeah, yeah, so on and so forth. Okay, like that. So basically it will be uh, I think n minus 1 factorial, right? Okay, so this is the whole logic. First we have to identify these distances. Okay, first we have to calculate this sh value and we have to keep it. The story is not yet over. So this is one step. Okay, so we are going to identify, like in a given what you call Pareto optimal front, all the solutions are of equal importance. That is, they are non-dominating each other. Now, for performing reproduction, how are we going to differentiate between them? Like how we are going to say that one solution is better than the other one, so that we can select the best solution for the next round. Okay. So for doing that, first we have to do this. So we have to identify sh of dij for all the combinations. We'll keep it. We'll keep it separate. Once this is identified, then we will calculate something called as niche count. So this niche count we have to calculate then. This niche count we are going to calculate for every solution. So xi is one solution. For every ith solution we are going to calculate the niche count. So this niche count we are representing it as gamma. Gamma of xi is equal to sigma xj belong to pk. pk is nothing but one front. Okay, so we are considering only the solutions which are lying in a given Pareto optimal front. So for our convenience, let us assume pk is equal to k is equal to 1, which means it is the first Pareto optimal front. That means the solutions which are ranked 1. So all the solutions that are of rank 1 will be in the first Pareto optimal front. So what the algorithm says in the sense, so lambda of xi, that is the niche count of the ith solution, is nothing but sum of all sh of dij, where what is j? I is the solution for which you want to calculate the niche count, where j is all the other solutions in this same font. Okay, in the same front, right? So we know all their sh value, right? We know everybody's sh value. We know because in the previous round we have calculated. That is, we have calculated sh of d12, sh of d13, so on and so forth up to sh of, if there are 10 solutions, sh of d1 comma 10, everything we have calculated, right? So this step, what it says in the sense, if you want to calculate the niche count of uh, first solution, then what you have to do is you have to add all the sh value. Okay, that is the shared, what is sh, shared sharing coefficient value, sharing coefficient value from ith solution to every other solution in that front. Okay, so that is you have to perform sum of sh of d12 plus sh of d13 plus sh of d14, so on and so forth, up to sh of d1 comma 10. So this is what we are going to do. So that is what the niche count of uh, ith solution. Okay. Right. So the shared fitness value of xi is then. So now based on this we are going to update the fitness score of ith solution. So now the shared fitness value of the ith solution will be, it will be new value, f I dash is equal to f by this niche count. I mean, okay, this niche count, where f is the original dummy fitness value. Previously we assigned dummy fitness value. Dummy fitness value will be same for all the solution in the front. If this dummy fitness value is 1000, then f will be 1000. Then 1000 divided by this niche count, that is gamma of xi. So now when you do this, now every individual will get a different fitness score. Okay, so this is how the algorithm differentiates between two individuals in the same font. Okay, so it will, now it will have a unique fitness score for everybody, right? So this is the whole logic, how it works, right? So let us not go beyond this. I think this is enough here. Okay, so to summarize, what we are trying to do in the sense, in a given Pareto optimal front, all the solutions are of equal importance, that is they are non-dominating. So they will have the same rank, and also their dummy fitness score will be same. Now when we want to go for reproduction, we want to differentiate these individuals. So for differentiating, first what we have to do in the sense, first you have to calculate the sharing coefficient. So sharing coefficient will be calculated between every individual and every other individual. That is, so we'll be calculating sharing coefficient like sh of dij for every individual using this formula. So once it is calculated, then we will calculate the niche count for every individual. So the niche count for every individual is calculated based on the sharing coefficient. So once the niche count is calculated, then the new or the updated shared fitness value for xi is calculated like this: fi dash is equal to f by lambda xi, where f is the dummy fitness score and lambda is the niche count of the ith solution. Someone summarize what we are doing here? Yes. Is this clear or not? Yes. You want me to repeat? Why? Hmm? No, only the last part I want. How this sharing coefficient is being calculated? Yeah, yeah. Every possible two solutions. Hmm. Otherwise it will be 0. What is t shed? Yeah, maximum phenotype distance allowed that we consider. Hmm, hmm. This each count for every solution. Yes. How do we calculate that? Yeah. Hmm. That is basically it is the distances between from the current solution to other solution, right? Based on this, now we are going to update the new. Yeah, it is by using what? F by. Yeah, what is F? And gamma of xi is the niche count of that particular solution. Okay. See, in the Fi, yeah, gamma of xi is there. F is the dummy fitness value, and gamma of xi is the niche count. Okay. Fine. So that's it about this algorithm. So whatever the rest of slides is also explaining the same thing. Um, okay. So there is another algorithm which is actually an improvement of NSGA, right? So this is also basically similar to NSGA, that is non-dominated sorting in genetic algorithm. That is what it is. It is the next version of NSGA, which is called as NSGA 2. But see, these both these algorithms are proposed by the same researchers. They are actually Indians. So basically, this work is from IIT Kanpur. So you can see they are all professors in IIT Kanpur. So this is an improved version of NSGA one, which is called as NSGA 2. It has also another name. It is otherwise called as elitist multi-objective genetic algorithm. It can be either called as NSGA2, that is non-dominated sorting genetic algorithm, or it can be called as elitist multi-objective genetic algorithm. Okay. So actually this is, you can say this is a much simplified version of the previous algorithm. It is very easy to understand and also very easy to implement when compared with the previous algorithm. Okay. See, the overall logic of the previous algorithm, what it says in the sense, whatever the, you take all the solutions, identify the first non-dominating front. For that it uses a technique, that is it checks every solution with every other solution. Si is compared with sj. So basically here we are comparing, in the sense we are minimizing, we are assuming all problem as minimization problem. So suppose if Si is, if the ith solution is less than the jth solution, then we will add that to a set. Yes, to the, we will add j to the set. J will be added here. Okay, j will be, or we'll call it as I. Yeah. So ij will be added to this set. Otherwise, we will increment mj. If ith solution is less than jth solution, then we will increment n. Okay. So yeah, no, if ith solution is yeah, if ith solution is better than jth solution, what's the algorithm says? Basically, n will be 0, right? N will be 0 if I is dominating everybody. Okay. So suppose if ith solution is dominating jth solution, if ith solution is dominating jth solution, then jth solution will be added to s. Else, that is if I is not dominating j. If j is dominating I, then we will increment n. Okay, initially n will be 0. Like that, we will compare ith solution with every other solution. So once this round is over, if n is equal to 0, if n is equal to 0, then what does it mean? If n is equal to 0, I. So I is, so it means I is dominating everybody. right? If I is dominating everybody, then what will be the rank of I? If I solution is 1, that is, it is available in the first optimal front. It is available in the first optimal front. Like that we do for every solutions. So for all the solution you do that. Then for every solution you see for which of the solution n is 0, we will put it in P1. That is the set P1. So set P1 contains all the solutions which will be in the first non-dominating front. Okay. Now once we identify the first non-dominating front, we will remove that from this set, okay, from the original set, and then we will do identify the second non-dominating front, so on and so forth. So that is how NSGA version 1 works. But NSGA version 2, it's a very simplified technique. It's an improved version of NSGA 1, that is NSGA 2, which is otherwise called as holistic multi-objective genetic algorithm. So here what we do in the sense, before going to the algorithm, let us consider these parameters. So P represents the set of solutions. So P contains all the solutions. Xi and Xj represents any two solutions. P dash represents the set of solutions in the non-dominated front. So in each round we have to identify the P dash. Initially P dash will be empty. Okay. So this theory is nothing but the same as the algorithm. So let us go through this algorithm. So initially P contains all the solutions x1 to xn. These are the set of possible solutions. Okay. And at the starting point, P dash will be null set. P dash will be empty. It won't have anything. At the end of the algorithm, P dash should contain all the non-dominating solutions. That is, it should contain all the solutions which are lying in the first non-dominating front. Okay. So what we do is initialize P dash equal to xi. That is, whatever the first solution, we are assuming at first P dash is empty. Now what we are doing is we are going to keep first solution. Let us assume x1 I am keeping in P dash, and I don't know, P dash should contain only the non-dominating solution. Currently I observed only the first solution. I don't know whether it is non-dominating others or not, but still we are moving that to P dash, and we are making this counter j equal to 2. Okay. And then what we do is compare ith solution, compare xi with xj. Okay. So this is xi, this is xi, that is x1 which is moved here, right? Okay. I think this should be 2. Assume it is 2. Compare xi with xj. Okay. So so what does it mean? It means that, or let it be 1 itself. Okay. But in the previous round we are setting it as j equal to 2. I think one of them should be I. Let us not much look into this. Just see this. So what it says in the sense, basically you have to compare this is currently I solution. This solution should be compared with every other solution. So you cannot compare it with itself. Okay. So you, for example, if xi, if j is 1, then you cannot compare x1 with x1 itself. Okay. In that case you should ignore, right? Those details are not mentioned here. But the point is you compare xi with the next solution. So in that case we are going to compare xi with xj, right? If xi is less than or equal to xj, then delete xj from P dash. Okay. So we are going to minimize. Our objective is to minimize. So we have to check whether xi is less than xj. That is, you have to check whether x2 is less than x1 is less than or equal to x2. Suppose if x2 is less than or equal to x1, okay, if that is the case, then first you have to check whether x2 is in the P dash or not. If x2 is in the P dash, you remove it. Otherwise you don't do anything, because only the non-dominating solution should be here. Now x2 is not non-dominating. Okay, so that we are saying you remove, right? Okay, that is the point. Suppose suppose if x1 is less than or equal to x2, then x1 should be here, okay. If x2 is less than or equal to if x2 is greater than x1, then x2 should not be here, okay. That is the logic, right? I guess I am not confusing you. So it's very simple. What it says in the sense, initially we are taking, so let us take an example. Let us assume initially p is this, so we are moving x1 here. So when you can move here, only if x1 is less than or equal to every other solution, then only we can move here, okay. But still at the first time we are moving, then what we do is we are taking x2 first. Next, what solution available? X2. So you compare x1, is x1 is less than or equal to x2, check. If x1 is less than or equal to, if x1 is less than or equal to x2, then no issue, because x1 is dominating x2, which means it should be here. Like that we have to check for every other solution, whether x1 is less than or equal to x3, whether x1 is less than or equal to x4, so on and so forth, up to whether x1 is less than or equal to xn, or let us assume x10, okay. But in between, say for example, x1 is not less than or equal to x5, say this is the situation you faced, which means what? X1 is not dominating x5, which means x5 is dominating x1. It means that x5 is less than x1, okay. So in that case, our assumption, this is initially an assumption, it is an assumption that x1 is dominating all other solutions, so that we kept here. But in this case our assumption proved to be wrong, so x1 should be removed, x1 should not be in p dash, okay. That is what the algorithm says, okay. So at the end of the first round, we will come to know whether x1 will be in p dash or not. If x1 is dominating everybody else, then x1 will be in p dash, otherwise x1 will be removed from p dash, okay. Is this clear? Is it clear or not? Yes, Akila, could you summarize what we are saying? Yes. Yeah. Hmm. Yeah, good. Okay, like that we have. So this is in the first round. Say assume that in the first round x1 is less than or equal to all xn. So it is valid to keep in p dash. Okay, right? So once that first round is over, then we confirm that x1 should be in p dash. Okay, if x1 is in p dash, then at the end of first round what we do is we will remove x1 from p. Now x1 will be removed from p. So a solution will be either in p or in p dash. It won't be in both the places. Okay, is it clear? Does it make sense? Because p dash xi x1 is dominating everybody, right? So we want to identify the dominating. So p dash is nothing but the set of solutions in the non-dominating front. Now x1, as x1 is dominating everybody, so x1 we already moved to p dash. So which means that x1 will be removed from p. Okay. In the next round, what we do? In the next round to p dash, we will be adding what? X2 we will add. Okay, then what you have to check? Then again we have to do the same process. Whether x2 is less than or equal to x1, whether x2 is less than or equal to x3, so on and so forth. We have to check until x2 is less than or equal to xn or x10. Okay. So if x2 is less than for everybody, then x2 will come here, right? Suppose if x2 is not less than something, then what should happen? From where? If say x2 is greater than x7, then what should we do? Then x2 should be removed from where? P dash, but it should present in P. Yes. Okay. So like that, after completing n rounds, what will be in P dash? So this is for x1, for x2, x3, so forth, so on and so forth. You have to do this operation for n times. When you repeat this for n times, what will be in P dash? Yeah, set of all the non-dominating solutions will be available in P dash. Okay, that is the set of all non-dominating solution in the first front. Am I right? No, 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 no. This is, see, when the first round is over, when the first round is over, we will get, when the first, yeah, that's correct. Okay, so basically we will get the set of all the non-dominating solutions, right? So that is what the algorithm says. Okay, so now let us go through the algorithm. If xi is less than or equal to xj, okay, then delete xj from P dash if it is already there. Okay, we don't know whether it is there or not. So if it is already there, it should be deleted. If it is not there, then just leave it. If j is less than P dash, then increment j by 1 and go to step 3. Okay, that is, if j is less than P dash, P dash is, we set a maximum count. Okay, so it is not that you have to identify all the non-dominating solutions. You can have a maximum count. So that here we are using P dash. So basically what we want to identify the individuals with good fitness score. So you can have some restriction on P dash. For example, we can say that I want to identify the top 10 best solutions or top 5 best solutions. Then we can set that count of P dash as 10. So this we will repeat then only for 10 times. Okay. Otherwise, ideally, the algorithm says that you have to repeat it for n times, but you can restrict it. Okay. So, if j less than P dash, then increment j by 1 and go to step 3. Okay, that's what it says. So this is the case if xi is less than or equal to xj. If xj is less than or equal to xi, then increment I by 1 and go to step 2. So if you identified one solution, if you have identified even one solution which is better than xj, okay, then there is no point in no point in checking further. Okay, there is no point in checking further. So what it says in the sense, say for example, first solution you take, we are checking whether x1 is less than or equal to x2. Say it is less than. Say x1 is less than or equal to x3. Say it is less than. Say when you come for x4, say x1 is not less than x4. x1 is greater than x4. Okay. So should we keep x1 in P dash? So x1 will be removed. After that, should you check? Should you continue this checking process? Should you again check whether x1 is less than or equal to x5? Is it required? No. Why? Why no? Because the objective is to find what? Whether, yeah, whether x1 is dominating everybody or not. That is what we want to find. Okay. So already it came to know that x1 is not, x1 is dominated by somebody. So you can stop here. So that is why we are doing here. Suppose if xj is less than xi, then increment I by 1 and go to step 2. So that means you need not continue further, right? So the control will come to step 7. The control will come here only if xi is dominating every other individual in P. Okay, control will come here under which situation? Only if xi is dominating everybody else. Okay, so in that case what we do, insert xi in P dash. We are inserting xi in P dash, and P dash is equal to P dash union I. That is whatever, that is insert in the sense it is union operation, right? So whatever the previous P dash, to that this I solution is also added. Okay, if still I is less than n, then again continue this same process. Go to the first step. Otherwise, output P dash as the non-dominating front with the current population. Right. So if P is equal to null set, if P is not equal to null, again continue. Right. So that is what the whole algorithm says. Okay. So this is how this algorithm work. Actually, this algorithm is better than the first version. The time complexity of this algorithm is order of mn square, and in the worst case, it is order of mn cube. Okay. Whereas NSGA one, that is non-dominating sorting genetic algorithm one, its time complexity is always order of mn cube. Okay. So the algorithm is further refined here. Let us the actual implementation is done like this. Let P be the current population. If P is the current population, first we are going to create some offspring population Q from P using genetic operators. Here we are not considering any Pareto optimal or nothing. It is normal using normal genetic operator like crossover, mutation or something. We are going to double the population size. If the size of population P is n, then we are going to create another n population. That second n is called as Q. So the total size of the population will be 2n. So this new population Q is created on P by performing some genetic operators like crossover and mutation. Right? The two populations are combined together to form a total large population R of size 2n. Right? Now we are going to apply the non-dominating sorting procedure to classify the entire population R. Now we are going to apply the NSGA2 algorithm on this R. Okay. After non-domination sorting, the new population P will be obtained. So after performing the non-domination sorting, again we will reduce the population to P. Okay. By fitting the non-dominated front one by one until P dash is less than P. Right. So here certain things you should remember carefully. See P. What is P is this represents count of P. Count of P is n, whereas count of R is, what is count of R? What is the size of R? What's the size of R? Size of R is 2n. Okay. What is R? Actually, what is R? R is a combination of Q and P. R is a combination of Q and P. Okay. So this algorithm will repeat how long, in the sense it will repeat until P dash. P dash is nothing but the set of non-dominating solutions until P dash is less than P. Okay, that is until P dash is less than n. Okay, so it should be less than n, so that is it will be exactly equal to n minus 1. It should not be equal to n even, right? Okay, so let us discuss this with an example. Yeah, with this diagram I think it will be clear. See, initially this is the population, the set of initial solutions, or P. The size of the population is P. Okay, so I mean the population is called as P, its size is n, right? Now from this P we are going to create another set of population that is called as Q. So the size of Q is also n. Put together their size is 2n. So 2n is nothing but R. So either you can call it as 2n or you can call it as R, or you can say R is equal to 2n. Now on all these solutions, on all these 2n solutions, we are going to apply NSGA2 technique. Okay, that is a non-dominating sorted genetic algorithm 2. So whatever we have discussed so far. So what the algorithm says? The algorithm says that initially you yeah, before that there is something I think we missed here. I'm sorry. Okay. See, basically the algorithm is going to identify all the non-dominating front, right? So this F1 corresponds to the first non-dominating front. F2 corresponds to the second non-dominating front. F3 corresponds to the third non-dominating front. Like that, it will identify all the non-dominating front, right? It will identify all the non-dominating front, right? So, in the first round, the algorithm will identify all the solutions lying in the first non-dominating front. Then it will identify all the solutions lying in the second non-dominating front, third non-dominating front. Like that, basically it identifies all the non-dominating front. But we need only p dash solutions. The size of p dash is n. We need only n solutions at the end. We are not going to take all the solutions. Okay. So the question is, how we are going to accommodate exactly n. P dash should be less than n. As per the algorithm, p dash should be less than n. It should not be even equal to n. P dash, the size of p dash should be less than n. Okay. So how are you going to ensure that? So probably this entire F1 you can accommodate here. This is the first front. So all the solution from the first front will be moved. All the solution from the second front also will be moved. All the solution from the third front also will be moved. But this front, if you see, in this case, you may not be able to move everything. So you have to move a partial solution from this front to this front. To P dash. So now this is a Pareto optimal set. It means everybody is of equal importance. They are non-dominating. Now, how are you going to exactly identify so many solutions to move? Some set of solutions to be moved here. That is, somebody should be ignored. If you want to take some solutions out here, then how we are going to ignore that? So we cannot do that arbitrarily. So we are not going to arbitrarily do that. So that is what this diagram says. So we cannot move this entire block also, because we want a partial set here, so that it will be exactly less than n, right? Now we want to take only few solutions, and those few solutions should be moved. Okay, for that we are going to use a technique called as crowding distance. We are going to use a technique called as crowding distance. So in the rest of the algorithm, that is what we are going to discuss, right? Okay. So this is the overall view of the algorithm. So initially what we are doing is combine P and Q and create R. So R is equal to P union Q. Perform a non-dominated sorting to R and identify different fronts of non-dominated solutions. Okay, so we identify different non-dominating fronts. So the first non-dominating front is called as F1, second non-dominating front is called as F2, so on and so forth, right? Set new population P dash is equal to null. Initially P dash will be null. Set a counter I is equal to 1 to indicate the front to be filled to P dash. Okay, fill P dash. So we want to move things from this after making this, identifying this non-dominating front, individual non-dominating front, we want to move from here to P dash. So when you can move, fill P dash until P dash plus Fi is less than n. That is Pi union Fi and I is equal to I plus 1. Okay. Otherwise, suppose you want to move a particular P dash, but if you move it fully, so if you want to move a particular Fi, but if you move it fully, you cannot do that. Then P dash will overflow. But the condition is P dash size should be always less than n. So in that case, we have to move a partial set. So if you want to move a partial set, then you have to follow a technique called as crowding distance, which will tell us like exactly which values can be moved from Fi to P dash. Okay, right? So only those values will move from Fi to P dash. Okay, so after moving those values, so they are considered as elite group. So this is considered as elite group, because from this total 2n we have ignored n. So this is considered as a elite group. Okay, then what we do, then we create offspring population Q dash from P dash, like how initially we created Q from P, then once again you create Q dash from P dash. Okay, and repeat all the above steps until convergence is done. If convergence is done, stop. So this is how the overall algorithm works. The next part what we'll be discussing is how this crowding distance is to be calculated. Right? So before that, could someone summarize what we have discussed so far? Yes. Hmm. Yeah. Hmm. Hmm. Yeah. Then what we will do? Then we will apply NSGA 2 directly, right? And we will identify what previously how we discussed the NSGA2 algorithm. We will identify different Pareto optimal front, set of solution lying in the first Pareto optimal front, second Pareto optimal front. Like that, we will identify all the solutions. Are you getting? But after that, we want to move few solutions to P dash. How many solutions we want to move to P dash? P dash should contain, yeah, number of solutions in P dash should be less than n. So, what should we? So obviously we know that the solution in the first front is better than the solution in the second front. And the solution in second front is better than the solution in the third front. So, we have to move the first front. If it is less than n size, then we can move the entire front here. Second front. Then before moving the second front, you have to check whether the after adding the second front also will the size of P dash will be less than n. If that is the case, we can move. Like that, we will keep moving. But when you come to one particular front, what will happen here? What's the problem we'll face? Yeah. So we have to move some set of solutions. Yeah, we have to move the partial solution. Now this partial solution cannot be moved arbitrarily. For that, what technique we have to use? Yeah, crowding sort, or we have to calculate something called as crowding distance. So based on this crowding distance, we are going to decide like which solution should be moved. Okay, so that is what the remaining part of the thing we are going to discuss. Okay, so what is crowding sort? So how are you going to do that? That's what we'll continue next. So the crowding sort basically it uses two concepts. One is called as, first we have to calculate something called as crowding distance, which is called as crowding distance metric. For every solution, we will calculate something called as crowding distance metric, or D. And then we will use a crowded comparison operator. This is a special operator. This is like normally comparison operator is less than, greater than, so on and so forth. This is not the normal comparison operator. We are going to use a special comparison operator. This comparison operator is called as crowded comparison operator, and it is denoted as less than symbol subscripted by E. Okay, so these two things we'll be discussing. So we'll be discussing individually like how crowding distance metric should be calculated. After calculating the crowding distance metric, how should we use this crowded comparison operator? Okay. So basically the crowded sorting procedure involves two steps, that is calculating crowding distance metric and then using the crowded comparison operator on this metric. Okay. So the crowding distance Di of a solution Xi is a measure of the search space around Xi which is not occupied by any other solution in the population. Okay, it is just like a population density. Di is lower. Di is lower for a dense population. Okay, Di is lower for a dense population. That is, if di is low, then it means that the population is more dense. Okay, if di is more di is low. Okay, if di is less, then it means that population is more. If di is greater, then it means that population is not dense. Okay, so basically what it does in the sense, uh, xi is a measure of this search space around, I mean di for a solution xi is a measure of the search space around xi which is not occupied by any other solution in the population. Okay, say for example, there is a solution here, there is a solution here, there is a solution here. Okay, say for this solution you want to identify what is the di. Okay, then the algorithm what it says in the sense, you have to identify uh, the area which is not occupied by any solution. So it means it is this area, something, not exactly something like this area. Okay, why we are not including this? Because the definition what it says, for this solution only we want to identify the distance metric. So it represents the area which is not occupied by any other solution. Okay, so you should identify the next nearest solution. So if this is the next nearest solution, then up to that border only you have to go. You should not include that. Is that clear? Okay, now if this area is lesser, if this area is small, then what does it mean? Population is dense or population is not dense? If this area is small, then the population is denser or not denser? Population means all solutions. It is dense because it means that some other individual is very close to you, so that your crowding distance is small. Okay, if this area is large, then it means that the population is not dense, right? Okay, so this is a overall, I mean, idea like how we are going to calculate the exact procedure we'll be discussing. Okay, next we'll be using the crowded comparison operator to compare two solutions and to find the winner. So first we'll be identifying the distance by, this is the logic. This is not the specific logic. At generic level, this is the logic. We are going to identify the area around the solution which is not occupied by any other solution. So that will give the understanding about the value di, that is the distance metric. Like that, we have to identify the distance metric for all solutions. If there are 10 solutions, then for all the 10 solutions, you identify the distance metric. Then we will be comparing every solution with every other solution based on the distance metric using this crowded comparison operator. And then we will be identifying like who is the winner. So this is here is the definition for the crowding comparison operator. So it's only for the comparison operator. So crowding comparison operator, it is defined like this: a solution xi wins a solution xj. So only for, so comparison operator, normally comparison operator is applied for only two solutions, right? So here the comparison operator is called as crowding comparison operator. So the crowding comparison, so when you apply crowding comparison operator on two solutions xi and xj, you can say that xi wins over xj under if all these conditions are satisfied. There are three conditions. If these three conditions were satisfied, then only you can say that xi wins xj. Okay, so if and only if means what? All the three should be satisfied. The first solution, what it says in the first condition, what it says in the sense, xi should have better rank than xj. Okay, that is, the rank of xi should be better than xj. Here better in the sense what? It should be less than xi, the rank of xj should be less than the rank of xj. That is the first condition. Okay, second condition, what it says in the sense, suppose if xi is having the same rank as xj. The first condition says that xi should have better rank. Second condition is, suppose if xi and xj have the same rank, then xi should have a better crowding solution. Then the crowding solution of xi should be better than xj. Okay, right? So uh, so I mean, this is not a separate condition. This is nothing but this condition is represented here in a what you call mathematical term. That's it. If rank of xi is equal to rank of xj, it is if xi is equal to xj's rank, then di should be greater than dj. That is, di is nothing but the uh, that is it is not nothing but the crowding solution. How much it is crowded. Okay, so that is what is called as di, how much it is crowded. So di should be greater than dj, where di and dj are the crowding distances of xi and xj. Okay, right? So that is what this algorithm says. Okay, not algorithm, that is how we are going to use the crowded comparison operator. Okay, so when you use crowded comparison operator on two solutions xi and xj, we say that xi wins over xj under these two conditions. The first condition is if xi is having a better rank than xj. The second condition is if xi is better than xj, then you need not look for the crowding distance. It is not required because it is in a different front. Okay, so the second condition is if both xi and xj are having same rank. In that case, we have to check the crowding distance of the solution I and j. So if the crowding distance of I is better than j, then we say that I is winner. Okay, otherwise j will be the winner. Okay, so there are two conditions. The first condition is xi should be better than xj. So the first condition ensures that xi lies on a better optimal front. So if xi rank is better than xj, it means that xi is in the better front. Then obviously all solution in this front is better than this front. Okay, in that case you need not look for the crowding distance at all. Only when you go for the solution that are lying in the same front. If two solutions are lying in the same front, in that case only we have to look for the crowding distance. The second condition resolve the tie of both the solution being on the same non-dominated front by deciding their crowding distances. Okay, so with respect to NSGA2, only second condition is valid, as we are interested only on one front. Okay, so whether NSGA1 or NSGA2, what we are discussing, there is no question like comparing, there is no question like which solution in this front and this front is better. We already know, based on the rank, we know that this solution is always better than this solution. Okay, if you want to maximize both f1 and f2, right? Only the question is in the same front, how will we differentiate? Okay, so this first case is actually not applicable for NSGA2 because we are interested only in a given non-dominant front. How are we going to differentiate the two solutions? Okay, so what we have to do is we have to do it based on the crowding distance measure. So this rule, it is only for how to use the operator, how to use the comparison operator. Still we have not discussed how to measure the crowding distance. So this is the actual logic of measuring the crowding distance. The crowding distance measure di is an estimate of the size of the largest cuboid enclosing the point xi, okay, without including any point in the population. The crowding distance of a particular ith solution, we call it as di, is an estimate of the size of the largest cuboid enclosing the point xi, that is xi is the ith solution, without including any point in the population, that is without including any other solution. Say for example, these are the solutions. Here is a solution, here is a solution, here is a solution. Okay, say for our convenience, here is also a solution. Okay, then the what it says, say for example we want to identify, say this is xi, say this is xi, we want to identify this solution's crowding distance. So the crowding distance di of a particular solution xi is an estimate of the size of the largest cuboid enclosing the point xi. So what is the largest cube you can draw here, or what's the largest cuboid you can draw here? So that is the, what do you call, that is the di, that is nothing but the measure of di. So this is the largest cuboid we can draw here, because the condition is the largest cuboid that you can draw enclosing xi without including any other point or without including any other solution. So if I draw any other, can I say this is the largest cuboid around xi? Two cuboids I have drawn, say C1 and C2. As per this definition, which is correct, C1 or C2? Why not C2? C2 is larger than C1, right? So why not C2? Why not C2? What's the reason? Why we are ignoring C2? Yeah, without including any other point. So if you include this, if you consider C2, then other points were included. Okay, right? So this is how we calculate di. Okay, so exactly after identifying this cuboid, the algorithm, what it says in the sense, you have to identify the height and the width of the cuboid. So what is the width and what is the height, and just add that. For example, if the height is 4 centimeter, if the width is 5 centimeter, then it will be 5 plus 4, 9. That will be the value of d1 or di. I is the ith solution. Okay, so this is how we calculate the crowding distance measure. Okay, right? So basically crowding distance, why we are calculating? Because if you want to select multiple solution from the same front, then how we are going to differentiate. Okay, so here if you go to your original story, that is from this front we want to move only few solutions, but all these are in the same front. Okay, so all these are of equal importance, so we are going to identify some better solutions out of this. For this we are calculating crowding distance. Again, calculating crowding distance, it includes two steps. What are the two steps? It include crowding distance metric and comparison operator. Okay, so what is crowding comparison? By using crowding comparison, we say that xi wins xj if xi has a better rank than xj. Otherwise, if xi's rank is same as that of xj, then the crowding distance of xi should be better than the crowding distance of xj. Okay. So how to find the crowding distance? So the crowding distance di of a particular solution xi can be estimated by drawing a cuboid around xi without including any other points. Okay, so that is how we calculate the crowding distance. So here is an example. This example is on based on a two-dimensional solution and also based on three-dimensional solution. Okay, that is here we consider I mean the first case is a two-dimensional one, the second case is a three-dimensional one. That is, in the first case we assume there are two objective functions. In the second case we are assuming there are three objective functions. Okay, so first let us see this simple case. Say this is the solution x2 for which we want to identify the di, that is the distance value, okay, crowding distance value. So what are its nearest solution? See, assume this is the nearest, these two are the nearest solution, xi minus 1 and xi plus 1. So what you have to draw? You have to draw the cuboid without including any other solution. So this is the resultant cuboid which you have drawn without including any other solution. So now you check the height of this and width of this. So that is nothing but h plus w, that is nothing but the d2. Okay, because in this is second solution. So this is how we calculate the crowding distance for this particular point or this particular solution. If it is a three-dimensional space, that is if the objective function contains three functions, so here we are assuming there are three functions, f1, f2 and f3. Now this is the point xi for which you have to identify the what you call di, that is the crowding distance. So again identify the nearest solution. So this is one nearest solution xi plus 1, this is another nearest solution xi minus 1. Now the cuboid is, it is length, width and height, three things. Okay, so there is a height parameter, this I think this you can take it as height, this you can take it as length. Okay, and also width also you have to consider, this is the width. Okay, so you have to add all these things. So height, width and length, add all these things, h plus w plus l, so that will be what is called as di. Okay, so like that you can look for n dimensional space also. So if it is a two dimensional space, we add only two parameters. If it is n dimensional, you may have to add n parameters. Okay. So in figure A, so whatever we have discussed, that's what it is explained here. Okay. So in figure A, it's actually a rectangle, whereas in figure B, it's a cuboid. So given a set of non-dominating solution f and the objective functions f1 to fm, the procedure to calculate the crowding distance for each solution xi belongs to f is stated below. Okay. So I is equal to f. So f is nothing but the, count of f. Okay, which is nothing but the number of solutions in f. Okay. For each xi in f, initially we set di is equal to 0. Initially there are all solutions, the set of solution is I. Initially we set di as 0 because initially we don't know what is their crowding distance score. Then for each objective function fi belong to f, fi is equal to sort of f comma I, that is sort all solutions in f with respect to the objective values of fi. Okay, so this will result in f1, f2, fm. So basically what it says in the sense, see, initially we have a set of solution I. Okay, now there are many objective functions f1, f2, f3, so on and so forth, like that up to fn. There are multiple objective functions. Okay, see here what we are discussing is, actually we are going to discuss like how we will calculate the distance metric for an n dimensional function or for an n dimensional problem. If it is a two dimensional, we can do that with a rectangle. If it is a three dimensional, you can do with a cuboid. If it is a n dimensional, how will you do that? Okay, so that's what this algorithm is about. So this algorithm is calculating the crowding distance for a n dimensional problem. So what it says in the sense, first solve the problem for the using first objective function alone, and then sort it in ascending order. Sort the result in ascending order. Result is in solution. So first solution, when you apply the first solution, each one is a solution, right? Already initially we have the set of solutions. When you apply the first solution, what is the fitness score? When you apply the second solution, what is the fitness score with respect to f1? When you apply the third solution, what is the fitness score with respect to f1? Only f1. And sort it in ascending order. Okay, so that set is called as this capital F1. Similarly, then solve the problem using only f2. And when you solve the problem for f2 only using the second objective function, what is the fitness score for the first solution? What is the fitness score for the second solution? What is the fitness score for the third solution? Again sort this in ascending order. Okay. So f2 is nothing but the problem is solved using the second objective function and it is sorted in ascending order, like that, so on and so forth. f3, like that we do up to fm. Okay, because totally we have m objective functions, right? So we create different set f1, f2 up to fm. right? See all these, so totally we have some set of solutions, but in each of these f1, f2, fm, the order will be different, because here it is with respect to the first objective function it is sorted. So whichever the solution, or whichever the individual which performs better for the first objective function, that will be at the top, and whichever the uh, solution which performs worst for the first objective function, that will be at the last. Similarly, this is sorted based on the second objective function, like that. Sorting based on the third objective function, like that we identify different sets. Okay, now to calculate crowding distance, so this is for crowding distance for an uh, multiple objective function. If there are m objective functions, then how to calculate the crowding distance? Then to calculate the crowding distance, we use this formula. For each solution j, which is equal to 2 to I minus 1, we are not considering the first solution and the last solution, that we will discuss later. So from the second solution to I minus 1 solution, I is the total number of solution, I minus 1 solution, what we do is, this is how we calculate the distance metric. dj is equal to sigma k equal to 1 to m, where m is the number of objective functions. Sigma k equal to 1 to m, f k into j plus 1 into f k into j minus 1 divided by f k max minus f k min, where f k is the kth objective function. For kth objective function, what is the maximum value? Okay, I mean, what is the maximum fitness score? Which solution is giving the maximum fitness score, or what is the maximum fitness score? And fk min is nothing but for kth objective function, what is the minimum fitness score, right? Like that we calculate. So let us take one example. Assume j is equal to 2. Assume j is equal to 2. Then for j equal to 2, it will go from k equal to 1 to m. Say k is equal to 1. If k is equal to 1, what it is going to do? What is fkj plus 1? K is 1, j is 2. So it is 1 into 2 plus 1. What is that? 3. Okay, that is the third solution minus f k into j minus 1. This is fitness score. Fitness score of the third solution minus f k into j minus 1. K is 1, j is 2. K into, it is 1 into 2, 2 minus 1 into 2 minus 1. What is that? f1, right? f1 divided by fk max. So initially k is 1. For first objective function, when you apply the when you solve the problem only considering the first objective function, what is the highest fitness score? Some solution will give the highest fitness score, right? What is that? So that is max. So let us call it as generally max minus min. Okay. So this is only for k equal to 1. Similarly, what will be k equal to 2? J is same. See, k should go from 1 2 into, that is f 2 into 2 plus 1. What is that? No. First perform multiplication. Always multiplication is higher priority, right? So what is that? 2 into 2 plus 1. 5. f5 minus f4. K is 2, j is 2. This is 2 into 2 plus 1, 4 plus 1, 5. 4 minus 1, 3, right? 3 divided by max. Like that you have to go on calculate up to k equal to m. Okay, when k equal to m, it will be fkm plus 1 minus fkm minus 1 divided by max minus 1, right? All these things you add. All these things you add. That is what this says. That is what is called as dj. That is the distance metric for second solution. Okay. Similarly, you have to identify the distance metric for third solution, fourth solution, so on and so forth. Right. So like that, we have to identify the distance metric for all the solution. Okay. What will be the distance metric for the first solution and the last solution? The first solution and the last solution distance metric will be infinity, because they, see, you consider this. See, this is the first solution. Okay, can you draw a bounding box for this first solution? If you draw a bounding box, at one end it will be unending box. Are you getting? It will keep on go. This both the ends it will keep on go. Can you stop at some place for this one? Are you getting the point? How will you draw the bounding box for 4? 4 is one solution. How will you draw the bounding box for 4? For calculating distance is nothing but bounding box, right? The bounding box for 4 will be something like this. Okay, for every solution we can draw the bounding box, but for the first solution and the last solution we cannot draw. So that the crowding distance for the first solution and the last solution is infinity. Is it clear? So for in this case, for which solutions you cannot draw the bounding box? In this graph, for which solutions bounding box cannot be drawn? 1 and 7. For all other solutions you can draw a bounding box, right? Okay. So this is how this algorithm works. Okay. So once crowding distance for all solutions is found in the last acceptable front, okay, then f is calculated. We have to select n minus p dash solution from f to complete the size of p equal to n. Okay, so this is, go back to the original story. The original story is our objective is to find p dash, right? Already we have applied this particular algorithm, and we have identified different front 1, front 2, like that. We have identified all the front f1, f2, f3. But when you finally add one particular front, you cannot add the entire thing. You have to add a partial thing. For that only we thought of calculating the crowding distance, right? Now we have found the crowding distance. So now already f1 is added, f2 is added, f3 is added. In f4 only a partial set should be added. So what should be the size of the partial set? It should be n minus p dash, because finally what should be in n? What should be in p dash? I mean, how many solutions should be in p dash? P dash should contain n solution. Okay, I mean it should be less than n. P dash should be less than n. Already it contains some solution. So again, how many more we can add? We can add n minus p dash. That many we can add from f2 to complete the size of, what do you call, to complete the size of p equal to n or p dash equal to n. Okay, you can call either p equal to n or p dash is n, because both are what do you call, both are 2n means if n is moved here, then the other will have n, right? To do this, we are going to perform something called as tournament selection operation using this crowding comparison operator. Okay, so crowding comparison operator, yeah, you can call it as less than e or c. Previously it was denoted as c, but c previously it was denoted as e, but c is more appropriate because it is, c stands for crowding comparison. That is, we select xi over xj if xi is less than, if xi, that is we select xi over xj if di is greater than dj. Okay, so if the crowding distance is larger, we select. Okay, if the crowding distance is larger, then the population is denser or not denser. If di is greater than dj, then di's population is denser than dj or it's less denser than dj. Yeah, good. So it is less denser than dj. So we are selecting basically a population which is less denser, which is in less denser area. That is, it is not denser. That is, there is no nearer individuals. Okay, so that is how we calculate here. So note that we prefer those solutions which are not in the crowded search space. Why we are doing this? To ensure population diversity. Okay. See, generally, because in other solutions already you selected from other font. This operation we are doing only for the front where there is a issue is coming, like we have to move only the partial solution. Already in other front all the solutions were selected. So probably they are in a they are in a more crowded region. Okay. So better if we select these solution from less crowded area, so that there will be diversity. So why we are doing this means to ensure diversity. Why we are going for diversity? Because you, the more diverse the population it will be more better. Okay. Diverse solutions are considered as better solution, right? So these are some of the remarks of this algorithm. NSGA2 is an elitist approach. So why it is an elitist approach? In the sense, initially we create 2n population, from that we take only n, that is we reduce to a large extent, so that it is called as an elitist approach. It is considered as a faster non-dominated sorting procedure with time complexity of order of mn squared when compared to order of mn cube of NSGA. With respect to time complexity, it performs better than NSGA. It does not require explicit sharing concept, rather than using a crowding tournament selection with time complexity of order of mn log n. Okay, so there is nothing like sharing the fitness score. In the previous algorithm, we used to share the fitness score, and then we calculate some approach for identifying differentiating the individuals in the same optimal font. Here all these are not required. So that also reduces the time complexity. So the time complexity in identifying the crowding, okay, in identifying the crowding distance or performing the crowding tournament selection, the time complexity is order of mn log n. So the overall time complexity of NSGA2 is order of mn square, right? So that's it about this particular algorithm, and also that's it about our discussion on MOOPS, that is multi-objective optimization problem. So with this we'll be stop discussing MOOPs. The next class onwards we'll be moving on to neural networks. Let us stop here. Okay, so before that, to summarize, in this algorithm, what we are doing, first we select an initial population P, okay, then from P we create Q, so which is of size 2n, then we apply NSGA2 technique, and we identify the set of solution on different non-optimal, I mean non-dominating font like F1, F2, so on up to Fn. Okay, but we want to identify only P dash solutions. So we check whether F1 is less than P dash and P dash should be less than n. So whether F1 is less than n, the size of F1 is less than n, then move F1. Okay, can we move F2 also, such that the total size of P dash will be less than n? If that is the case, move. Like that you keep moving. But when you approach one particular F5, what will happen? We cannot move the entire thing, we have to move partially. So now we have to identify the partial solutions which is to be moved. To identify these partial solutions, what should we do? To identify this, yeah, we should calculate crowded sorting or crowded distance. So for calculating crowded distance, we need two things. What are they? We need to calculate what? We use two things. What are they? We have to first calculate the crowding distance, which is called as DI. Yeah, and then we use crowded comparison operator. Okay. So what is so when you use crowding comparison operator, when you say that a solution xi wins over xj, when you use crowding comparison operator, when will you say that the solution xi wins xj? Two. Yeah, if xi is better than, if the rank of xi is better than xj, then xi wins. Otherwise, yeah, in that case, what should we do? If rank of xi is equal to xj, then how will we decide the winner? In that case, yeah, whose crowded distance is better, they wins, right? Okay, then how do we calculate the crowded distance? For calculating crowded distance, what we should do? For a solution xi, how will we calculate the crowded distance di? What we do? We what is the logic? We identify the nearest solution. You identify the nearest solution and basically your cuboid such that any solution. Okay. So based on this, so if it is a two-dimensional, you have to add the height and the, yeah. If it is three-dimensional, you have to add the, if it is n-dimensional, then what should we do? Yeah, by using this approach. Okay. Before doing all these things, first you have to solve the problem using every objective function. Okay. First solve using first objective function and then sort it in ascending order. Then solve using second objective, solve using third objective, like that. Okay. Then we'll follow this approach, right? So, so when will you say that a particular solution is better than another solution? If di is greater than dj. So if di is greater than dj means it is less denser. di is less denser, which means it is more diverse.